Brandon, that's okay. We're gonna go over some of the stuff we did last class, and then the problem sets are technically due by the end of the week, but again, it's do as much as you can. And if you have any questions, feel free to reach out. The math form was just a survey to see how much everyone knows in terms of math, preferably as soon as you can, but we already pretty much looked at the results. You should still submit it though.
I think we should just post the classroom code then.
All right, so real quickly, while you guys go ahead and join the Google Classroom, we let people roll in. I wanted to one more time address last class because I've taught ScioVirtual for a few years now, and that was kind of the most distracted I've ever seen a class. And I don't mean to say that in like an insulting way. It's summer break and you guys are having fun, and that's great. But I think there are students here who actually do want to learn optics and do want to actually gain something from this. And when the chat is exploding with messages about really just random things, and it makes it difficult for those students to learn and for those students' questions to be heard. So if you are here to learn, please ask questions, ask frequent questions, ask seemingly dumb questions. We want your questions because that helps us to help you. If you're confused, others certainly are too. This is an easy material, and so we want to help you. But if you aren't here to learn, whether that's because you think you already know everything or because you're forced to be here by your parents and you want to play Overwatch or whatever, don't distract those who are here to learn. So please keep the Zoom chat clean. Don't, yeah, just if you don't want to pay attention, that's your choice. But please don't let that choice impact others. So yeah. And this thing at the bottom is really something that I want you guys to keep in mind. Even the smartest of you who have won your International Physics Olympiad and your SciOly medals or whatever, I can guarantee you will learn at least one thing from this class. That's my objective as a teacher. It's our objectives as teachers. So pay attention. I promise you we will do our best to make sure you actually get something out of this. And yeah. I'll give you like one more minute to get the Zoom code in, and then I will give it to Arthur.
Just still people joining, so.
Yeah, so for last class, I tried to record it. I have no idea what happened, but I can't find the recording. So we'll review everything we talked about last class today for a good amount of time. And hopefully, because I know last class, a lot of you guys also struggled to understand what was going on. It was pretty math intensive. And so hopefully our review today will help with that. And today's is being recorded. I've made sure of that, and I will post the recording.
So are we gonna address homework questions today?
We can do
I'd
that
like-
at the end if we have time.
Yeah, okay, because I had like 2 questions.
So we can, if we have time, we'll get to those at the end. And I guess if there are homework questions, I am not limited to 4 p.m. So those of you who need to go, the class will be done by 4 p.m. But if you want to stay and just ask a question or two, I'll still be here.
And if you ever have questions on homework, you can email the teachers as well.
Yeah,
you
can email or like Google Classroom, leave a comment anywhere. We'll find it.
Arthur, do you want to screen share?
Sure. Here. Can everyone see the screen?
Yeah.
All right, cool.
Yeah.
So today we're going to start with mirrors and lenses, which is a pretty big part of geometric optics. We're going to start by reviewing stuff that we did last class. That was the Google Classroom code and the beginning slide. First thing that we saw last class was the law of reflection, which dictates specular reflection. Specular reflection, I don't know if we mentioned that term last time, but it's when the light ray gets reflected in exactly one direction, as opposed to diffuse reflection, which means it's reflected in every direction, and there's no clear law of reflection. So, does anyone remember key steps when we were proving the law of reflection? Just anything we want to throw out? Does anyone want to restate the actual law of reflection, which is, I know, somewhere on the screen, but does someone want to explain it or why it works?
I think they're saying it in chat. You have chat open.
Okay, that's my bad. I did not have chat open. I see Pythagorean theorem. I see trigonometric ratios. Yeah, some good stuff that we have. We remember that there's one principle that we left from. Does anyone exactly? Fermat's principle of least time, which says that light will always take the shortest path to its destination. I see some of you remember derivatives. That was just one line. Let's not think about the derivatives too much. It was just one line that we needed to explain for Fermat's principle, where we're minimizing the path. But apart from that, it's really just trigonometry that we use to prove it. Yep, that is true. All right, so we seem to remember the law of reflection pretty well. It just says that the incident angle, which is always with respect to the normal, which is always perpendicular to the surface, will always be the same as the angle of reflection. It's pretty simple, pretty neat. So after that, we had the law of diffuse reflection. And it's when light diffusely reflects everywhere. There's no clear place that it reflects to, because that would be specular reflection. Those are the two types of reflection that we have. On the left, we have specular reflection, and on the right, diffuse reflection. Do you remember the proportionality? That was a little bit
Lambert's cosine
law. Yeah. So that was yeah, that was part of it. That would explain it. It was that one diagram with all of the slices that we would take, and then every slice would have a different part of the intensity, overall making the ray itself. And then we had the law of refraction, Snell's law, which dictates when light goes from one medium to another. Does anyone want to explain how this works? Do we remember what the index of refraction is? What it represents? Yeah, go ahead, Benjamin.
How much light bends in a medium?
Yeah, so the law of refraction does say that, but the index of refraction specifically tells us how fast light moves in a medium, and in a way how optically dense it is. I know optical density has multiple definitions, one of them being related to absorption, which we'll see later. But the index of refraction says how fast it moves in a medium, and when it changes mediums, it bends. And actually, there's a really interesting analogy that we can think of when we want to predict where light is going to go and how much it's going to bend. Let me see if I can have a laser pointer here. Hold on, give me a sec. You guys can see. Why is the laser pointer? Yeah.
Click L.
Laser pointer's not working.
Wait, just try clicking L. Isn't that like the keyboard shortcut?
Clicking the L?
Yeah, just clicking L. No?
No, it doesn't work.
Oh, you're on the slides, right? Oh.
Yeah. Oh, well, it's fine. I'll just use the pencil. So we see here, we're going from some medium. Can you guys all see this? Right? This line. We're going from N1 to N2. And if you think about it like a tank with the chains rotating on both sides, right? We have one rotating here and the other rotating here for a little tank. If we think about it, when we get to this intersection, if this material here, N1, the light travels slower than in N2, meaning that N1, the index of refraction is greater than N2, then when we get to this changement in medium, this side of the tank is going to start rolling faster. This acts right, because this side, the left side, lags behind, and that's an analogy for how you can predict light to bend. And with that analogy, does anyone want to predict how light is going to bend in the second diagram over here? Is it going to be closer to the green arrow or the blue arrow, given that the index of refraction of the gray medium is higher?
I think it will be the blue arrow.
It will indeed be the blue arrow. Well, again, if we were to draw our tank here, since the index of refraction is greater in the bottom medium, then it's going to slow down a little bit, and it's going to be the blue arrow. And we can triangulation. Let me see if I can go back to Google here and move this around so I can actually.
Why is
stop
it the green
here.
arrow?
Here, we see that if we were to trace this ray diagram, when you have a greater, here, let's erase everything. If we have a greater medium with higher index of refraction, if we were to trace the ray directly, this is where it would go straight, right? But since in this medium, the index of refraction is higher, meaning that the velocity inside of this medium is greater. Oh, sorry, there's a notification somewhere.
Was that Duolingo?
Here in this case, right? Yeah, that's some device in the background. It would rotate this way, since this one would travel faster. Does that make sense? If we think about the equation itself, which is N1 sine theta 1 is equal to N2 sine theta 2. We know that if we have N1 being equal to 1, we can just forget about it. If N2 is greater than N1, and this remains constant, if sine theta 1 remains constant, if we increase N2, we have to decrease sine theta 2, and thus we have to decrease theta 2. So we also see that relationship mathematically. And if we were to invert the roles and start with air going to air, well, in this case, we see that since it travels faster in air, if we want to go back to the tank analogy, this side of it is going to travel faster, and thus we're going to swing this way from the direct direction of the ray. So we saw how it works mathematically, and again, I'm going to send this simulation if I haven't already, so you guys can play around with a visualization of the indexes of refraction. I think it's a really good simulation to get a sense of how it all works. But does everyone understand how refraction works and how it bends light?
Yes.
All right, cool. Let's go back to the slides. And let's erase everything. All right, so last thing we saw last time was the critical angle. Now we saw that the critical angle happens when we go from a medium of higher index of refraction to a medium of lower index of refraction. right? We had some sign condition that would dictate when the angle is at the critical angle, which means that the light undergoing refraction is going to be parallel to the surface and it doesn't exit the medium. Any angle beyond that, any incident angle beyond that, is going to make it totally internally reflect. So does anyone want to answer this question about the critical angle? Does it exist from a medium with n1 to a medium with n is equal to 1.5? Is it possible for there to be total internal reflection when you leave from a medium which is equal to which has an index of refraction equal to 1 and going to 1.5? You guys are right. You can't have that. And if you think about it mathematically, the sine function, the inverse sine function can't take in a parameter that's higher than 1. So 1.5 over 1 would give an error, and that makes sense because that can't happen. So we've looked at what happens in all types of incident angles, right? If you're going from a medium of higher index to a medium of lower index, if it's smaller than the incident, if it's smaller than the critical angle, then we're still going to have refraction as normal, which is shown right here. If it's at the critical angle, it'll be directly straight. But if it's greater than a critical angle, we see that this angle theta1 is greater than this critical angle, then it's going to be totally internally reflected, and we can think of this as the law of reflection, where theta1 is going to be equal to theta2, which is exactly what happens here. Does that make sense to everyone? All right, cool. That's we've just covered a lot of last class really fast. So here are two practice problems that we're going to take a second to look at. Let's calculate this and let's see your answers in chat, or if you want to speak up. That was a mistake. I'm going to give it a second here.
Yo, yeah, let's not send our answers in the chat. If you have an answer, send it to one of us so we'll tell you if you're right. But we don't want people seeing the answer before they finish. So. Like you can privately message it, but don't send it in the full chat.
Okay, so I've received a lot of answers. Let's go over it real quick. So let's think about what's going to happen here. I saw a lot of right answers and I saw some incorrect answers. So let's just go over it. So we have an angle, incident angle, theta, which is equal to 37 degrees. And there you go. And then we're going to have some angle here that we want to predict. So already we know that since we're going from an index n is equal to 1 to n is equal to 2.5, since this index of refraction is greater than that one, we know that we have a lower angle here for theta2. So any answer above 37 degrees is already going to be off, and we know that from the tank analogy, if we want to think about it that way. So which law do we need to solve this? Snell's law. So we have the index of refraction of air is 1. So 1 sine of 37, I'm sorry, I'm not that good at writing on the computer. I hope it's still legible, is equal to 2.5 sine of of our theta 2. So if you rearrange that equation, we have sine theta 2 is equal to sine 37 over 2.5. Now all we got to do is invert that sign. So theta 2 is going to be equal to the sine inverse of that same stuff, which I'm not going to take the care to rewrite because I'm very bad at writing on the computer. And that is going to be equal to 14 degrees, or technically 13.9, but 14 degrees. All right. If that makes sense for everyone, let's try the second problem.
And if you don't know the trigonometry to like do inverse sine or the sine, please contact one of the teachers so that we can help you out with that. Because these are pretty
Absolutely.
unescapable things in optics. You do need to know how to
Yep.
do sines and inverse sines. So.
Absolutely. Again, at the end of this class, I'll still be here if we want to go over some trigonometry, but you should absolutely reach out to us if sine, cosine is something you haven't seen in math yet, and that's okay. But we can't really dodge that in optics. So we're going to have to deal with it and learn it so that we can deal with these problems. What is the formula for the index of refraction? Here, I'll post it up here. The formula is n is equal to c over v, where c is the speed of light and v is the velocity in the medium. Why is it called c and why is it called v? Well, v is just the velocity in the medium, and c is just a universal constant. It's just like it was just defined by scientists that way. Constant, yeah, it is constant.
Yeah, apparently the speed of light is c. Yeah, because it means swiftness or celerity. I've never heard of that before. That's pretty weird.
Yeah, we don't really need that.
Yeah, if you guys took quantum last year, you saw all the weird names physicists like to use. So the only people who can match physicists in weird naming of things is statisticians. There's in Bayesian statistics, there's a thing called the Indian buffet process and the Chinese restaurant process, which are both made by a very hungry statistician, I think.
All right. Are we ready to look at this problem? I see a lot of people slightly confused. Yes, so let's calculate the index of refraction first. Here, I'll erase all this. I'll erase all this. And then for those of you who have the answer, here, I'm just gonna, there you go. The answer is 21 degrees. Now let's see how we get there. So we had n, I'm gonna write up here again. N is equal to c over v, which in this case, we're leaving from medium, which is air. We're leaving from this medium of 2.5 to a medium where you travel 0.6 times the speed of light. So we're gonna have c over 0.6 times the speed of light c. C cancels out, and we have 1 over 0.6, which can also be written as 1.666 repeating. So that's the first step. We've determined the index of refraction of the new medium that we're going to be traveling to. So now it's just a matter of applying Snell's law one more time. And oopsies, there you go. And now we're going to do just that. I'm going to erase that up here since we already have that and make myself some more space. So we're leaving with 2.5 because sine of this case 14 degrees. And if you're asking yourself a question, well, we entered that medium, right? Why is this angle the same as the angle of incidence for the new problem? Well, if we're to draw a normal here, since these two lines are parallel, these two angles are going to be the same. They're alternate angles, so they're going to be the same. So we can use that as our new angle of incidence and put that in the equation. 2.5 sine of 14 is going to be equal to 1.666. We don't need that much precision. Sine of theta 2 or theta 3 if we were to change this problem. It doesn't really make sense. It doesn't really matter. So if we're to rearrange this equation again in the same way, we're going to end up with sine inverse of, in this case, you just divide both sides by 1.66 of 2.5 sine 14 over 1.66. That's going to give you 21.278. And that's our answer. This one's a little bit trickier, right? We had to find the index of refraction of the new medium, and then we had to calculate how much the new angle is going to be. Does this make sense to everyone? I just used calculator. Yeah, if you have a you'll need to use a calculator here. I don't think you can compute the sine inverse of 2.5 sine 14 over 1.66 in your head. If you can, that's really impressive. Oh, if you didn't, yeah. The keyword was then enters, but that's okay. We should have made it clearer, yeah. It probably is possible, Toby. All right, so let's keep going. I'm gonna pass that on to the next instructor.
All right, so does anyone want us to like go over again anything we just reviewed for repetitiveness, for hearing it one more time? Okay, well, no is an unhelpful answer. If anyone has a yes, then say yes, but if it's a no, then don't say no.
Again, if you haven't understood it, chances are someone else hasn't understood it either. So really do make sure you ask your questions.
You
'cause
can
you're probably
even
doing-
sorry.
Yeah. Oh.
You can even private message an instructor with something like that, because we would prefer you say it to not say it. That's not embarrassing. It's you should be proud of that. Anyways,
There's nothing
Well-
worse than finishing a class and then knowing that all your students didn't understand anything.
I'm not getting anything, so I'm just gonna start. So in ray optics, it really all comes down to how good your diagrams are. Drawing a good diagram can immediately solve you a seemingly very complicated question, and it's really the most important step in any question. We're gonna talk about a bunch of complicated lens systems and like fancy words like catadioptric systems, but the reality of it is these things are all very easy questions if you can interpret what the words are saying and put that to a visual graphic. So you do that with ray diagrams. Rays are the trajectories that light travels in, and rays follow straight paths. Why do rays follow straight paths? It's not a trick question if anyone has an answer.
Fermat's principle.
Yeah, that's exactly it. It's straight paths are the shortest distance from one point to another, and that's because of Fermat's principle. And we've really already used ray diagrams. Like for this, the law of reflection, that's a ray diagram in itself. Refraction, we're drawing ray diagrams of things refracting through a medium. And so it's nothing special about them. We're just tracing where light goes from one point to another. See the next slide. However, not all rays are created equal. You don't want to draw every ray that radiates from an object. If I were to do that here, how do I draw? If I don't know how to draw on here, but if I were to do that here, you'd have rays coming out from every point, every direction on this object. And in reality, not all the, what he's doing right now, not all these rays are useful. Some of them just go to nowhere. And although light is going in that direction, we don't really care about that light. We care about the light that's going to where we are trying to receive the image, right? And sometimes that'll be called a focal point. Sometimes that'll just be where our receiver, our person is looking at something. It really just depends on the context. And so with this little guy over here, we're only drawing the ray that goes from our object, the apple, to our receiver, his eyes. So, yeah. Usually when we draw rays, focal points are for lenses. I mean, yeah, they can also be for other things. Focal point is a lot more general than that. It's also sometimes you won't even care about the focal point when looking at a lens. It all depends on your context. But rays are drawn from the bounds of what you're diagramming. So you can see if we're looking at this object, this bottle right here, we need to look at both the rays that come from the bottom of the object and the top of the object. And we can anyone tell me why we have 4 rays on this diagram and why all 4 of those rays are important?
Can I answer?
Yeah, go ahead.
Because the bounds is like the left eye and the right eye, and the other boundaries is the top of the bottle and bottom of the bottle. So those
Yeah.
4 rays capture all the vision.
Yeah, you got it exactly right. I think it's like bottom of the eye and top of the eye, but I mean you had the right idea. That's exactly it. So really, you won't even draw 4 rays most of the time. Usually you'll just approximate your eyes as a single point, and you'll just draw one ray going from the bottom of the sky to your eye, and the other one going from the top point of your bottle to your eye. And really, what is most important in these ray optics problems is determining what are the most important points in my diagram. Which rays do I need to be drawing? Because the more simple your diagram is, the better your diagram is, but you don't want it to be too simple so that you're not capturing the actual things that are going on in this in here. Yeah. So rays create real images and virtual images, okay? Real images are exactly what they sound like. They are an image that is real and its actual light is going there. So in this diagram right here, our object is at the blue dot, okay? And that's where our light is coming from, okay? And so the blue dot projects light onto the mirror and onto the detector. Okay. But then I guess I'm gonna answer the question. My bad. But that light blue is gonna be our virtual image. If you think about it, when I'm looking at a mirror, the light is reflecting to me, but what I'm seeing is not as if I have light on top of myself. What I interpret, if I was stupid and I had no idea what a mirror was, is that there's a guy standing over there inside this window, right? And so that is the virtual image of myself. Here, if you have a mirror in front of you, like if you can see my camera, if I'm looking at my mirror like this and at an angle, I'm gonna see it as if there's a guy beyond the mirror that's in that window. But in reality, the object's gonna be over here. Okay? It's hard for me to show this because I'm on a zoom camera. But the actual thing you're looking at in this image is the blue. But if you're stupid and you have no idea what a mirror is, you're gonna see that you're gonna interpret the virtual image as where the light is actually coming from. Okay? And so virtual images oftentimes are not, I mean, there is cases where they are certainly actual virtual images, but they are oftentimes better interpreted as virtual objects. And so you can see that light blue dot, that's what I would call a virtual object. It's where you would think your object is, but in reality, it's reflecting off a mirror. And these are very useful, especially in lenses for determining focal points, as you guys mentioned, but even in general for modeling, because mirrors are entirely uninteresting if we distill away the real image and look at just the virtual image. Does this whole slide make sense? Are there any questions, anything that I should go over again before we move on?
Here, I guess I'll add something. If you're asking yourself, is it a real image or is it a virtual image? You can think of it, as if you can put a film there, or you can put like some piece of something and see the image, then it's going to be actually real. But if it here in just like in the diagram at the bottom right, the lights get reflected. If it appears to be there, but it's not actually there, then it's definitely a virtual image.
All right. Oh, I think this is Luke.
So now we're gonna do a practice problem, virtual versus real. And on the top row, these are objects. And on the bottom row, these are images. So I want you guys to tell us which one of these are real and which one of these are fake or virtual images or objects.
Yeah, let's make sure to I guess it's too late now, but privately message the answers, not say it in everyone chat.
Yeah, but I think everyone's getting it.
They are.
So
Yes.
yeah, you guys are right.
Oh, there you go. No.
Oh,
Oh, well, I'm sorry. It's clicked
it's
a bit too
fine.
far there. You can.
And like in the previous slide, which said it's you can also think of virtual images as virtual objects. This is why we have a system of lenses where a virtual image becomes the next virtual object for the next lens.
Mhm. So this deals when we have like a system with many lenses, and if one of them produces a virtual image, then it'll be relayed onto the next one.
And now let's do a problem about seeing your reflection, basically. So an object is, yeah. So I want you guys to have a few minutes to do this problem on paper. And then maybe in 1 or 2 minutes, we can reveal the answers because I don't think it should take more than 2 minutes. Okay, I hope everyone's drawn a diagram and try to get the answers themselves. Now let's look at the diagram. So as you can see here, the mirror is a distance s away from you. And I know it looks weird because we haven't drawn the rays on all the bounds, but yeah. So I know that there's only one ray drawn, so it technically doesn't follow our draw the rays on the bounds principle, but we've still gotten the right answer here. So does anyone have any questions or can we move on?
Does everyone, in particular, does everyone get what the distance that you see yourself away is 2s?
Yes.
Why? So it's like what I said earlier. If you were looking at where that image was, like you had no idea what a mirror was, and you think, oh, there's something over there, it's a window, you would see it as being 2s away, right? And because as you get closer to the mirror, it looks like you're getting closer to, just purely logically without any numbers, as you get closer to the mirror, it looks like you're getting closer to yourself. As you get further away, you're getting doubly further away from yourself, right? Yeah, I mean, yeah.
I see people mentioning curved mirrors. Yeah, for curved mirrors, we would actually need more rays that are drawn from the bounds of an object, and then the image would be wherever those rays meet, if they do meet. And then if they don't, it's a virtual image, and we'll see how to deal with that next class.
And yeah, it looks like we've ended early, so if you want,
Oh, wait, we have a
We still have a Kahoot coming up, but
Oh,
here's
right,
your
yeah.
daily attendance. Make sure to submit that. And while you guys are doing that, I'm going to set up the Kahoot.
This class wasn't split, right?